Discover how fluids can remember their past motion, creating mysterious ripple effects that persist through time. When a droplet moves through fluid, it creates ripples and vortices that don't disappear instantly but persist, influencing future motion. Let's start by understanding what makes this phenomenon so unusual and counterintuitive. In typical fluid dynamics, we assume fluids respond instantaneously to applied forces. However, in confined microfluidic systems, the fluid's past motion continues to influence its current behavior. As a droplet moves, it leaves behind a wake of vortices and disturbances that persist much longer than expected. The force at time t depends not just on current conditions, but on an integral over all past velocities. The key lies in how momentum diffuses through viscous fluids. When a droplet moves, it generates swirling vortices in the surrounding fluid. In systems with moderate viscosity, these vortices decay slowly rather than disappearing instantly. The droplet is surrounded by layers of rotating flow that persist and influence later motion. The decay time scales with length squared divided by kinematic viscosity. In microscale systems, this decay time ranges from milliseconds to seconds, enough to create memory effects. One of the most striking examples is the walking droplet experiment. In a vibrating fluid bath, droplets bounce on the surface and create standing waves that guide their horizontal motion. The droplet creates waves beneath it, then literally surfs on its own wave field in a continuous feedback loop. Each past bounce contributes to the wave pattern, and this accumulated pattern guides the droplet's future trajectory. The droplet's path is a function of both its current state and the entire history of waves it has created. Remarkably, this classical system mimics quantum pilot wave behavior, showing interference and tunneling-like effects. Let's look at the mathematics behind hydrodynamic memory. The equation of motion includes both external forces and memory forces from past motion. The memory force is expressed as an integral over all past times, weighted by a memory kernel gamma. The memory kernel typically decays exponentially with a characteristic time tau, showing how older history matters less. This type of memory force is known as the Bassett history force in fluid mechanics. Several physical mechanisms create and maintain hydrodynamic memory. First, viscous diffusion spreads momentum slowly through the surrounding fluid. Second, confined geometries trap vortex structures that would otherwise dissipate. Third, surface waves can persist with decay times much longer than typical flow timescales. In confined spaces, the fluid has nowhere to escape, so disturbances recirculate and persist. Memory timescales either with viscous diffusion time or with wave oscillation period, whichever is longer. Hydrodynamic memory has important applications in modern technology. Micro-robots can exploit memory effects to swim more efficiently by riding their own wakes. In drug delivery, understanding memory helps control how particles navigate through blood vessels. Multiple particles can synchronize their motion through shared memory in the fluid medium. In biology, cilia and flagella coordinate their beating through hydrodynamic memory, not direct contact. The walking droplet system reveals a surprising connection to quantum mechanics. Classical walking droplets exhibit behavior similar to quantum particles, including interference patterns. These droplets demonstrate double-slit interference, tunneling through barriers, and quantized orbital states. This resembles pilot wave theory, where particles are guided by an underlying wave field. This suggests that quantum-like behavior can emerge from deterministic systems with memory. Hydrodynamic memory challenges fundamental assumptions in fluid dynamics. Classical fluid dynamics assumes force and velocity are related instantaneously through viscosity. The standard drag law says force equals negative gamma times velocity, implying instant response. But memory effects show that force actually depends on the entire history of velocity changes. The correct form includes an integral over all past velocities, weighted by a memory kernel. Time flows forward, but the fluid carries information backward from past to present. The fluid transforms into a viscoelastic storyteller, weaving past events into present dynamics. Let's summarize this remarkable phenomenon of fluid memory. Fluids remember their past motion through persistent vortices and waves that don't instantly dissipate. The memory timescale depends critically on viscosity and geometric confinement of the system. This has profound applications in micro-robotics, biological systems, and even quantum mechanics analogs. The droplet and its surrounding field form a unified system where past continuously shapes present. Even the most fleeting substances, like fluids, possess a form of persistence and memory. Every drop carries subtle whispers of its past journey through the fluid medium it inhabits.